So one of the things that you'll hear about a lot in electric circuits are fuses and circuit breakers. A fuse is set up in series with the circuit, and it's designed to heat up, and when it gets to a certain temperature, meaning a certain current going through, the fuse will actually melt and then force the circuit to be open. And this makes sure that there's no fire. That there's not a hazard with the circuit. There's something, because there's something wrong with the circuit. Circuit breakers work a little bit differently. If you look at the bottom here, the way the circuit breaker works is that there's a bimetallic strip. So current is passing through, right? Current is going through like this, going through, it's all connected, and it goes out. If the current's too high, that bimetallic strip will heat up, and if it heats up a certain amount, this side of it over here will extend further than this side, and the circuit will actually open. This will open. Now the nice thing with circuit breakers is, you can see the spring right here. You can just push this down. If you push this down, you can reenact this and then have current go back through again. The rule that we had for our airplanes when I was flight instructing was, if a circuit breaker popped, you're allowed to reset it once because maybe there was just a surge in the system or something. But if it pops again, we were not allowed to close it again because there's definitely something wrong with the circuit. If you have too much current going through, it's going to heat up and it can cause a fire in the end. Okay, so let's say that we have a circuit set up like this. We have, a hair dryer set up, we have a clock set up, a fan, computer, lamp, we have a 15 amp circuit breaker, and we have a 120 volt source. And we want to know, if we close the switch for the hair dryer, is the circuit breaker going to pop? And so in this case, we're dealing with a circuit with, power. And I'm going to see if you can figure out what to do here. You should be able to do that and determine if the circuit breaker will pop if we add the additional thing. So I'm going to, why don't you go ahead and pause the clip and give this a try. When you're ready to check, you can hit play to continue. All right, so again, 15 amps we've got there. So each of these is going to get a full 120 volts. This is all in parallel, so every single one of these is going to get a full 120 volts. The lamp is 100 watts, and we know the voltage, so we can figure out how much current's in there. And so 0.833 amps of current. If we look at the computer, it's got a full voltage. We have power, and we can get how much current's in that one. So 0.625 amps is going through that one. In the fan, same process, P equals IV, and 0.7967 amps. The clock is going to use 0.04167 amps. So the hair dryer would use 10 amps if we closed it. And in this case, if we add them all up, that would actually be okay. We would be underneath the 15 amps that the circuit breaker would have here, because if you remember, in parallel, right, the current is splitting, and so when it all comes back together here, this is going to be a full amount of 12.29 amps, right? And so if it's under the 15 amps, the circuit breaker will not pop. You probably experienced this in your house one time or another, where you've turned on an additional thing and the power goes out. That's because you have too much current going through, and you have too many things turned on in parallel, and the circuit breaker pops. All right, so ammeters are critical devices in electronics, and we're going to talk about how they're set up. So ammeters measure how much current's going through the circuit, and they're placed in series. And an ammeter has very, very, very low resistance, and we want it to be that way because we do not want to, the ammeter is a device to measure what's going on in the circuit. You don't want to put it in there and have it completely change what's happening in the circuit. It's a device to measure, how much current you have. So it's designed to have extremely, extremely small amount of resistance, so the current passes straight through. And for our ammeters, we've been assuming an ideal ammeter where it's not contributing at all to the circuit. You know, the resistance is infinitesimally small. So the way this works is you have current coming in, um, and then you have you know, a setup like this where you have essentially a parallel setup. You know, the R represents the internal resistance of the galvanometer, which the galvanometer itself measures the current. And then here you have a very small resistance as well. Now, what will happen is most of the current goes through this small resistance. And then some of it will go through the galvanometer, and this is calibrated so that, you know, the galvanometer will know how much current's actually going through. And the galvanometer will measure that current, and then you'll get that on your device. So these two things set up in parallel make it to where it's, you know, a really small amount of resistance. This is kind of neat. This is a you know, older way to measure current, and this was set up so that there's actually, you know, current passing through, and it's heating up the wire. And as it heats up the wire, the pivot here will move, and this thread, you know, will move, and so the spring will compress or contract, and based on how much it compresses or contracts, it will tilt the scale, and then based on the thermal energy that's going through, you know, it'll move the pivot a certain amount. And as it does, it'll give you how much current is actually going through. Voltmeters work differently. Voltmeters, you were trying to figure out how much potential there is between 2 points in a circuit. So, you know, we put it on either side of whatever object that we're looking at. So let's say we have a light bulb here. We're going to place it on either side. And the way that this works is you actually want a very high resistance. And if you think about it, right, if you've got current coming around, you pretty much want all the current to just pass straight through the light bulb. You really don't want any current, hardly any current going through the voltmeter. So what you do is you make the voltmeter extremely high resistance, so that pretty much all the current just passes through the light bulb or whatever you have, and the voltmeter doesn't affect the circuit. And we assume ideal voltmeters as we do our circuits. We assume that, you know, it's not taking any of the current or the potential there, and pretty much no current goes through that galvanometer. And so that's calibrated for whatever, you know, resistance that it has with the galvanometer to give you how much voltage that's being used around whatever spot that it's placed around. All right, so we have a circuit set up with a light bulb with a resistance of 18 ohms. It's hooked up to a voltage of 18 volts. The voltmeter is set up so that it has a high, but not infinitely high resistance. How would the current in the circuit change as compared to having voltmeter that has an infinite resistance? So let's draw what this would look like here. We have an 18 volt source, we have an 18 ohm light bulb, and then we have a 550 kilo ohm voltmeter. So I'm going to have you do that. You know, compare the two, what the current would be like, you know, if the voltmeter, like, it wasn't even there, it was an ideal voltmeter, versus what we've got here. And then you can compare them. So go ahead and pause the clip and do that. And when you're ready to check, you can hit play to continue. All right, so you know, if we look at infinite resistance, it would just be V equals IR. We would have 1 amp going through, and we'd have that. However, if we consider the voltmeter, and we have that in parallel, 1 over 18 plus 1 over 550,000, and we'll end up getting 17.9994 ohms. And let's see how that'll affect it. It's going to be a bit higher. It's going to be 1.000033 amps. Not very much though, right? So this would be a pretty decent ammeter. It's not really affecting the circuit a whole lot. We've got a little bit more current coming out than we would, but yeah, it doesn't affect the too bad. Potential dividers are really helpful if you have a situation where you need a varying amount of resistance, and like a rheostat kind of, you know, you have these in your house where, there's a little lever that you move back and forth and you can change the brightness and the dimness of light based on, the time of day. This is a setup where we have a metal bar here in the middle, and this bar is a conductor, and then we have a light in this case. It doesn't have to be a light, this could be other things. And we have this where we can move this back and forth. So, for instance, if we have it set up here, this would be the same as having a light bulb and part of this metal in parallel together, and then having this in series with it. If we need more resistance, we can move this over here, and we can just slide it over, and then it would be like having this. We would have this and this in parallel together, and then this would be in series with it. Or we can completely bypass it and have the current pass through the light bulb, then through that. And it allows us to have, a different amount of that voltage used up in the divider. And again, this can be helpful for, a situation where we need a variable amount of current going through a particular part. So what we're going to do here is we have a potential divider that's 2 meters long. Every 10 centimeters has a resistance of 1 ohm. If a 15 ohm motor is hooked up in parallel to the potential divider, how much power does the motor use if the circuit is set up so that the divider is halfway down? And then how much power does it use if it bypasses it? So let's go ahead and draw this out. We have our motor, and then we have our length here set up where, it's halfway down. And I'm going to have you try this one. You're going to work this as a complex circuit, and then you can figure out the power. And then once you do that, you can try part B as well, where it's basically the motor and then the whole bar in series with it. So yeah, go ahead and try that, and pause the clip and give that a shot. And then when you're ready to check, you can hit play to continue. All right, so 100 centimeters long. Every centimeter is 10 ohms. Well, I'm sorry, every centimeter has 10 ohms, and it's 2 meters long. So if it's 2 meters long, it's 100 centimeters. So every 10 centimeters has 1 ohm of resistance. So we have 100 centimeters, which would be 10 ohms, and then that side would be 10 ohms. And so this is essentially the picture what we've got. We've got a a motor that is 15 ohms. We've got this, which is 10 ohms, and then this, which is 10 ohms. The first thing that we're going to need to do is bring the 5 and 10 ohms together. Those together end up being 6, and then we can bring them all together for a total resistance of 16 ohms. And we can set up the current, and I forgot to give you the current. And the current is 20 volts. And so we've got that. And then, and then we can figure out the current 1.25 amps. And then we can go back one step and figure out how much voltage each uses. 7.5 in there, and we're just concentrating on the motor. So both of these, the bottom and the top, will both get 7.5, and the current passing through would be 0.5 amps. So we know the current, we know the voltage, and it's going to be using 3.75 watts. So if it completely bypasses it, we're going to have a situation like this. We'll have 15 ohms, 20 ohms, which is because it's 2 meters long, and every 10 centimeters has 1 ohm. So that's 200 centimeters, which would be the 20 ohms there. We add them up in series to be 35 ohms. We can use Ohm's law to figure out the current going through, 0.571. So we've got the current passing through, and we have the resistance there. So we can find the power, and so it would use 0.89 watts instead of what we found before when we used the potential divider.